Good morning. How is everybody? So excited for today. Good. Meteorologist Angela Buckman. I'm a local meteorologist in town. I work at the NBC affiliate, Channel 13. I'm a proud 96 Purdue grad. What a day to be a Boilermaker. Countdown is on until 9:20 as well. We've got a lot to get through between now and then, and we're really happy that you're joining us today. This is the total solar eclipse viewing event at the Indianapolis Motor Speedway, proudly presented by Purdue University. This event will allow three amazing organizations to come together. Of course, Purdue University, of course, the Indianapolis Motor Speedway, and NASA. We are celebrating this once-in-a-lifetime event. By the way, this is only one of 3 NASA locations in the country, so you are in for a treat all day long. You are in the sun track, by the way, and this is going to be a little more technical in nature. We've got scientists, engineers, astronauts that will all be presenting here today. Our live astronaut panel, hosted by This is Purdue podcast host Kate Young, will come a little later. It will feature 5 of Purdue University's Cradle of Astronaut members. We've got information that you're going to learn about, the Parker Solar Probe and how it's enabling us to learn more about the sun than ever before, how the James Webb Telescope is changing our perceptions of the galaxy, Neil Armstrong's world-changing Apollo mission, and NASA's aspirations for the Artemis campaign, Purdue University's Cradle of Astronauts, and how each member later today has taken their own giant leaps to explore space. And of course, the interconnectivity between space and motorsports. Our first panel, Closer Than Ever Before, Technologies to Touch the Sun, starts now.
Hello. We're live.
Right after you all, we'll go on.
Are you sitting here? Yeah, I'm listening now. Okay. All right. Thank you all so much for coming. We are so excited to chat with you this morning. My name is Nikki Rail. I'm the Associate Director for Flight at NASA headquarters in the heliophysics division. I would like to take a moment to have my panelists introduce themselves, and we'll go from there. And I'd like to start with Bryony at my right. Yeah.
Hi, I'm Professor Bryony Horgan from Purdue. I'm a professor of planetary science in the Earth Atmospheric and Planetary Sciences Department up at Purdue. I'm a planetary geologist, so I study the surfaces of other planets in our solar system, particularly the moon and Mars. I use the Mars rovers, like the Perseverance rover, to look for ancient habitable environments on Mars, and also study ancient volcanoes and impact craters on the moon as well.
And Heather.
So, hi, I'm Heather Futrell. I'm a program executive at the NASA Heliophysics Division, and I work on 2 current projects, Muse and Sunrise, both things to go explore our sun. And I've also worked on some of the operating missions as well.
Catherine.
Hi, I'm Carolyn Free.
Yeah.
I don't have mic.
All right.
Let's try that again. I'm Carolyn Free. I'm a professor at Purdue at the School of Aeronautics and Astronautics, and I work with satellites and space debris. And if you have questions, what's up there, what's coming down, what are we sending up, where is it going, that will be me.
So one of my favorite things about the sun is it's a system-level science. I'm actually a marine ecologist by training, so I kind of grew up doing research in the ocean, and it's very strange that I'm now working with spacecraft in the sun. But I would like to chat a little bit today about how this system-level science works, also just kind of how all our different pieces fit together and how we kind of in our different niches do some research that impacts sun. As you know today, this is a big day for us with the eclipse coming up, opportunity to visualize the corona. Weather's looking pretty cooperative, so I'm very excited about that. But I was going to start with you, Heather, and could you share a little bit about what NASA's doing and what we do, some of our missions studying the sun, some of the things we do in space weather. What's going on with you right now?
Yeah, so let's see. So talking about the corona today, so we have missions placed all over in space, and so one of those is actually going to be flying through the corona. It has been since 2021. So if anybody knows that project, it's called Parker Solar Probe. So it's the mission to touch the sun. And so that mission's pretty exciting because it's going faster than any man-made object's ever been, and it's also it's just so close to the sun, so close. In December, it'll be 3.8 million miles away from the sun. And that does sound like a lot, but our Earth is actually 93 million miles away from the surface of the sun. So it's getting really close. And then also we have projects like Voyager. So Voyager is actually outside of our solar system, and it's still and so it's still sending back data. Granted, one of them it takes like 23 hours one way, and the other one takes about 19 hours one way. But we have many missions scattered about. So,
And it is amazing. Like the Parker mission is incredible. It is. Sorry, we're having
they're coming in and out.
So the Parker mission is incredible. You know, the heat shield at the front, 3,000 degrees behind that, room temperature a few inches behind. It's incredible that the engineers have been able to accomplish with that mission. So I'm curious for my Purdue colleagues. Can you tell a little bit about the research you're doing and how that's kind of connecting into some of the studies we have with the sun? Karen, would you like to say?
Okay. Yeah, my research is not directly kind of looking at what the sun is doing, but more dealing, okay, what is the sun doing to us and to our satellites? For one, in my research, I'm using the sun to be just a cheap illumination source. So it actually shines on the satellites, not only gives the satellites power, but actually I can look with my telescope and then see the satellites, know where they are. And if we look at them long enough, we can even see, like, are they tumbling? Are the solar panels deployed correctly? Although the satellites are so far away that we only see like a bright dot, like a star. Besides that, the sun is also influencing us in kind of how the Earth atmosphere works and how drag on the satellites work. If we're thinking about space debris, during the solar cycle of high activity, the atmosphere actually expands and makes more of the debris burn up and clean up a bit more that space around the Earth. And then if we're kind of in a solar minimum, it's good for our missions. We're staying up longer. We need fewer maneuvers, but therefore also the debris is not coming down as fast. The other aspect, of course, is if we have kind of solar storms, coronal mass ejections. And that can actually disrupt things on Earth, but we are protected by the Earth magnetosphere from that. But also our satellites, as they are in a much weaker magnetosphere, as they're further out, they are much more affected. So we see kind of interference with the electronics during solar storms of our satellites. And if we would have a very large solar storm, then that could actually take out some of our satellites because of kind of arcing, and they go through differently charged plasma currents in that atmosphere. So we're looking at that and try to be prepared and try to be proactive so our satellites are surviving that.
Thank you. I'm curious, you may hear people in some of the broadcasts talking about Team Sun, Team Moon, Team Earth. It takes a few planetary bodies to tango. I'd love to hear a little bit more about your background and how, your perspective as a planetary.
Yeah, so I mostly work with geology, so this is really fun now. So on Mars rover, for example, I work on the Mastcam-Z camera. That's kind of the eyes of the Perseverance rover, and we actually do a lot of solar science with those cameras. We monitor the sun. We look at the sun almost every day to measure how dusty the atmosphere is. But that also gives us a chance to monitor the sun from a totally different place in the solar system over on Mars. And we get to track things like sunspots. We actually get to watch the Martian moons, Phobos and Deimos, these little potato moons that orbit Mars, do actually transit the sun and have eclipses. They're a lot smaller, though, so they don't block out the sun. But we can actually monitor that with our camera. And we've actually used those observations to help nail down the orbit of those moons, which is really important as we start planning for new robotic and human missions to visit them. So that's really exciting. But at a bigger scale, I like the idea of the sun as kind of system science, because a lot of the work we do is trying to understand things like the history of the solar system, trying to understand, for example, the sun hasn't always been as bright as it is today. We think it actually used to be a lot dimmer billions of years ago. And that may have actually been at a time when life was first starting on both Earth and Mars. And so understanding what the climate of Earth and Mars might have been because of the effects of the sun changing over time is one of the things we worry about a lot. You know, it's hard to start life when you have a cold, icy world because the sun was a lot dimmer. So we think a lot about the sun and how it interacts with the planets a lot at kind of the system level for the work we do.
Thank you. Thank you very much. So Heather, you know, not only are we here for this incredible eclipse today, I keep hearing about solar max. You know, tell me a little bit more about what is solar, hang on. Let me try and not drive everybody's ears crazy. Solar max, what's going on with the sun right now, and what is this maximum?
Yeah, so we have a 11-year solar cycle, and so we're approaching our solar max right now. So we're expecting the sun to be more active right now, so that's why a lot of us are super excited for this eclipse, because we had an eclipse that came in 2017, that was another total eclipse. However, the sun was not nearly as active. So we're expecting this time that when the moon blocks the sun, we're really hoping that we can see a lot more things popping around the moon, some more wispy and complex structures, hoping that the magnetic field, it should all be a lot more active. So we're really excited to see what we can during this eclipse today, during totality, which for the cloud cover, it looks like we should be good to go.
Absolutely, yeah, fingers crossed. So I wanted to share a little bit, you know, when the heliophysics division, we have a fleet of spacecraft that are orbiting around Earth and Sun all the way out to Mars, and as Heather mentioned before, in the far reaches of interstellar space with Voyager 24/7. I was just kind of curious if we could chat a little bit from your perspectives of like, why do we study the sun? Why is it important? I mean, obviously it governs our life cycle on Earth in many ways. It's when we wake up, it's when we go to sleep, it helps us with our immune system, our agriculture, energy, all these things, but there's a lot of other science. Sometimes I personally kind of take the sun for granted. It's always there in the morning when I get up, and you know, it's pretty darn reliable. But I'd love to hear Carolyn a little bit, if you could share a little bit more about, you know, why do you think we study the sun in general?
Yeah, I mean, I get it. We say the sun is far away, and as long as we get light, we should be good. But there's a lot more going on, and you see in the projection also kind of the Earth magnetic field lines that you see. So the sun is not only just giving us photons as light, but there's also a lot of charged particles going on, and then the mass ejections that go up, and then these charges interact with whatever other objects we have out there. They interact with the satellites, they interact with our atmosphere, and they interact with the Earth magnetic field. So depending on how active the sun is, it influences things on Earth, but most noticeable the satellites, just because they're further out and they are not as protected by the Earth magnetosphere. So a significant part of the research is that, for example, my colleague at Purdue, Ephraim Fischbach, is doing is on how can we predict when there are big solar storms or big coronal mass ejections, because we want to be ready for that. We want to have our electronics protected for those cases. And right now, it's just like this more or less random times when those occur. They're more active during the solar high, but but the exact times when a wave of charged particles comes to us is kind of hard to predict. And then for our satellites, we also want to design them that they are more robust. As they're traveling through different parts of the plasma, they're getting charged up differently, and then we can have so-called arcing, like little thunderstorms, so to speak, on the surface of the satellite. And if you ever shorted your cell phone or something, you know that's usually not going well. And so we have to have ways of protecting our electronics and keeping things that we like GPS and our weather forecast going, even when we have a very active sun.
So you're touching on some really cool things around space weather. You know, I found it fascinating that yes, indeed, there is weather in space, and that weather in space can impact us on Earth when it comes to things like communications, navigation, our power infrastructure. I don't know if anybody's like me. I'm visiting Indiana. This is my first time here. I'm using my GPS to literally go everywhere, and there are wonderful straight lines and no traffics, but I rely on that thing on a day-to-day basis. And so it's interesting when we think of as a society, you know, the technology that we rely on, how dependent we are with our star, our sun, and our satellites to cooperate. Heather, you want to share anything else that we've got going on in the space weather arena, or even as we look forward to putting humans further out in space, you know, some of the activities on Gateway?
Yeah. So yeah, so one thing that heliophysics participates in, it's a project called Moon to Mars, and so we have some instruments that are going up on a project called Hermes to help us study more about the star in an effort to make astronauts safer when we start traveling and going back to the moon and then eventually to Mars. So we are trying to better understand, and as Carolyn was saying, like we need to be able to predict what space weather is happening. And we do have some solar predictions already. They come from one of our partner agencies, the National Oceanic and Atmospheric Administration, or NOAA. But it's something that, because we still don't really understand all the effects that happen on the sun, we still need to be better about studying more about the sun, having more information with in situ where it's measuring directly in the environment. And so we still have more to do, so we can keep improving and making sure everyone's safe who's traveling in space.
So, Bryony, I'm curious, there's a lot of other planetary bodies out there that are impacted by space weather, that are impacted by the sun, and there's things that we can learn about our sun that also help us better understand other planets. And I'd love to hear any comments you have about what we can learn here in our own kind of solar neighborhood and what we can learn as we look outwhere.
Well, I mean, one of the things that we've can't tell. One of the things that we've learned from the Mars rover. So the human exploration side of NASA actually put an instrument on board the Curiosity rover, and that was to measure radiation dosage as the rover launched from Earth, traveled through space, and landed on Mars, and then operated on Mars. And that was really fascinating because it was. This is just totally finished. That was me. Yeah, and that was really fascinating because, as I was saying, we have an instrument on board the Curiosity rover that actually measured the radiation dosage coming from launching from Earth, traveling to Mars, and then landing on Mars and operating on Mars. And that was our first chance to really understand how much radiation an astronaut would experience on that trip to Mars. And so we found that it's actually even worse than we thought, and that's something we're still trying to figure out how to deal with. So for reference, if you go to the International Space Station, you end up with getting a lot of radiation from the sun and galactic sources. It's several times higher than like the DOE annual limit for radiation workers, right? And that's already bad. If you go to Mars, it's about 10 times worse. And if you operate on Mars, it's that same dosage again. So it's a whole lot of radiation. That's one of the things you want to understand more about. For example, how space weather and how it varies over time and through the year, through the solar cycle, how that might affect our ability to get astronauts in space safely and keep them there safely too.
How are we going to bring that into this connectivity?
I love you're touching on solar cycle, future exploration goals. A lot's going on right now with this eclipse, so we're getting into solar max. Like, should we be expecting to see anything different out of this eclipse because we are in solar max, Heather?
Yeah, so because we're in solar max, we're hoping that we'll see some more kind of magnetic structures and some more solar flares, maybe even with our naked eye during totality. So typically the sun can be a little bit calmer, but because of solar max, there could be more things that are kind of getting shot off and coming into space. So, yeah.
And I'm also curious, we've got a lot of, I'm familiar with the research we're doing at NASA. I'd like to chat a little bit about that we're doing today and some of the activities. But was there anything else you'd like to share from a Purdue perspective on anything you know going on or things are happening, or should we kind of jump into some of our NASA activities we have going on?
I mean, we collaborate with NASA a lot, and I think one of the things we have to keep in mind with those missions is kind of the different levels of complexity that go into it. I mean, one is kind of, okay, how do we plan? How do we find a good trajectory in the multi-body system, like from the astrodynamics where we want to go? How do we actually can be close to the sun and actually not run into the sun, but make a nice turn and come back? And then kind of a lot of research goes into the actually then flying the mission, the navigation. How do we know where we are? How do we know we are operational? How do we know that everything has deployed the way it should have deployed? How do we know we are healthy? And then a lot of my research is also, how do we make sure not to run into the stuff we brought up? Like we are kind of often have several thrusters and upper stages that are decoupling, and then we're throwing away stuff. And unfortunately, most of that
Focusing on
debris we are leaving
everyone
behind.
with
So
abilities.
it's also part, how do we not ram into the stuff we leave in orbit because it's orbiting with us, and how do we coordinate between the different missions that we can all be in that space, do the exciting research, and not get in each other's way.
I think that's what's so incredible for science and engineering in general. We do better science when we learn from each other, when we bring
To
these
come
disparate
and
data
help
sets with
me.
different ideas and different concepts together to really
Thank you
better
very much.
understand
So
our
now,
system and learn more
have
about our
someone that
star.
helps
So,
work as a
Heather, I'm going to look
consortium
at you
to-
again. We've got sounding rockets going up today, before, during, and after the eclipse. We also have some student balloon experiments going up. Can you share a
Universities.
little bit about some of the things we're actually going to be doing
And
in
that's very- tell
observations
us what
today during
looks
the eclipse?
like and feels like for you
Yeah,
today to be
so
that
for the
person, that
sounding rockets,
collective
yeah,
that
there's
comes
three that are
together
launching
to
from
bring us
Wallops,
united
Virginia,
today at the
and
eclipse.
they're going off about one 35 minutes before eclipse peak, one at eclipse peak, and then one right after. And they're going to be just studying what changes in the atmosphere, because there will be changes when the moon's blocking the sun, because we're going to have less heat. I don't know if you guys have looked at your weather apps, but if you can tell, there's actually a lower temperature during the time of totality because of that temperature change.
Rockets that fast. It is super difficult to get. I mean, we're looking at race cars today, but to get rockets going, 3 sets of rockets going within an hour and a half time period, it is an amazing feat, and that crew is incredible. It's just boom, 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 boom. And if anybody, I don't know if anybody's had the pleasure of watching a rocket launch, but a lot has to go right in a very short amount of time for that to work. And I'm super excited that we're getting 3, not only one bird up, but three rockets up in rapid succession.
And they did the same thing for the annular eclipse back in October out of White Sands, so they're a busy crew. And then another science activity we have going on too, so NASA has some WB-57 jets, and so there's going to be 3 jets that are going to be flying north as they go in order to expand their totality time frame, so that way we can continue to take more measurements with that totality time. It's such a unique time for a scientist, so we're really excited to get more information from those 2 different NASA experiments.
That is so cool. I can't wait to see the results and how that compares with our spacecraft. I'd like to talk a little bit about y'all personally. Brian, starting with you, like, what are you excited to see today? Like, what is your kind of like why for the eclipse, and what does that mean for you?
I've actually never seen a total eclipse before, so I'm really excited to see it for the first time. I'm so excited to be able to see the structures on the sun, be able to see the corona. I think that's just going to be so cool, a true like once in a lifetime event. Seeing it during solar max, even more exciting.
Barrett,
So
'cause
I'm
you have been
so
partners
excited to be
with
able to do
NASA
some solar system science with my eyes today. It's going to be very cool.
Partners with us here.
Such a good point, because I'm used to seeing all this amazing imagery. I've never seen a total solar eclipse ever before, totality. We see these amazing images from spacecraft, but today we get to be the telescopes, we get to be the observers. Heather, how about you? What are you most looking forward to today?
Yeah, so from the science side, I'll have to just take on what Brian was saying. Seeing the corona and being able to see those structures with my naked eye, I'm really excited for that. Also, from like a personal side, I did witness the 2017 launch, but I was out camping, so it was very different because you got to see a little bit more in terms of wildlife. But here, there's so many people here that are joining us. Like, I'm so excited to have this much energy about an eclipse, about science. This is awesome.
Thank you. How about you?
Yeah, so besides personally seeing the eclipse, of course, actually my students are out in the field and we are testing a new camera and seeing if it's a camera that is inspired by how our human eyes work, and it's not measuring the total light but light differences. So we should be able to look directly at the sun even before the eclipse, and we are hoping to see, okay, can we see some of the sun activity with a different type of camera, and that will be one of our biggest field tests at the moment.
Very cool. Well, you all today are scientists. You are curious. You are here to see this incredible phenomena. It's going to be interesting to see in this kind of very unique setting if we do see any of the wildlife effects or different sounds, but notice what's happening with your bodies. Like, I can't wait to see just like, the response, like, I've heard the hair stands on end on your arms, or, just it feels very kind of almost eerie, or some people it just feels very cool. So I hope you all can take a moment today to kind of just be really, check in with what it feels like for you and those around you, and as we experience this together. Heather, so I would like to chat a little bit more. Parker, you talked about it's doing its closest pass to the sun yet. You've been involved with Parker. I'd love to hear a little bit about just mission experience in general. Like, what does it mean to work a mission, at NASA? What does it mean to work on a mission studying the sun at NASA?
So for a mission studying NASA, it's about partnerships and collaboration. So there are so many people involved in the path of a project. So you've got principal investigators who will build together this proposal from a design concept, and then they propose to NASA. They go through a lot of rigor in that process before you're selected. And then once you start that, then you start building hardware, then you start integrating hardware, then hopefully you test it, everything comes out well, and then you do a launch. And then once you launch, you go up into space, and then you start bringing data down. And so there's this whole process kind of from cradle to grave for a mission. And then at the end of the mission, you have to dispose of it, because we have to keep our space debris limited as we can. So that's one of the other pieces that we're trying to do, and be good stewards of the environment that we're all investigating and researching still.
Thanks, Heather. Brian, so today is a big day, right? We've got the Eclipse going. This is incredible science. Like, what's coming up next for you? Like, what are the things in the coming days, and how does this kind of mesh or not mesh with your research in the coming days?
Oh, I can't answer that. Purdue going to the championships tonight. Go Boilermakers. Yeah, our fun fact for today is that this is the first time Purdue's in the championship since Neil Armstrong walked on the moon, who's also a Purdue alum, so great day. Anyway, but beyond that, I'm really excited. This is such a wonderful outreach opportunity. Space is such a great way to get, kids and everybody in the public excited about science, and I'm so excited to hear all the wonderful questions from everybody. We have a booth, EAPS booth for our department over in Gasoline Alley. Come check it out. If you want to ask more questions about space exploration, space missions, planetary science, please come talk to us. We're always glad to hear about that. If you want to talk to anybody about how to actually have a career in space exploration, we're all happy to talk to you about that. But I'm really excited for the impact this will have on STEM education, research in the years to come, because it's such an inspiring moment for sure.
Yep. I have one more question for you, Carolyn. You talked earlier about orbital debris and things that are going on. So we've got a lot of stuff in space right now, like a lot. And there's only going to be more and more satellites. And I'm curious any perspectives on why it's so important to be characterizing this done and looking at some of this stuff as space is becoming really, there's like some serious traffic jams up there. Like it's becoming very, very crowded.
Yeah, especially the near Earth space is very crowded, and like altitudes like 800, 850 kilometers are already space debris dominated, and not like satellite and cool science and communication dominated. So that is, of course, a big problem. And my aim is we want to do spacefaring. We want to have GPS. We want to have our weather forecast, which is satellite-based. We want to be able to launch kind of the cool missions to do further science. And then we have to just be careful on how we treat that environment, because for a long time we thought, oh, space is big and there's space for everything. But things are moving fast. Like the objects can move faster than kind of a bullet leaving your handgun. And then you can imagine there's a lot of damage when things run into each other. So so we have to be careful. And then what's next for me is, as we are pushing out further, like away from the near Earth space, more like closer to the moon again, which is super exciting, we also want to have good strategies on how we sustainably can use that space, so that we have many more decades to come to launch our missions and be able to operate the way we like it.
Thank you so much. And I was wondering if anybody has any questions for us. I think we have a minute or two. If anybody would like to ask a question, we'd love to hopefully be able to answer it.
There's a question there.
There's one over here.
There.
Yeah, come on up.
Here, I can give her a mic.
Okay.
Hi, sorry, just a very quick question. Are we able to see the camera that you're working on with your students?
Unfortunately not, because yeah, we need a bit more quiet space for that, not too many people and stuff. So I think many of the actual experiments are off-site. Sorry for that, but we're excited to share the results.
Any other questions?
Anything else? I can come to you if you've got one, even in the back.
the
Just
right,
raise your
right.
hand.
Well, you're left.
I see you.
Yeah.
There are lots of you now.
I will try to do that.
I was just wondering what technologies are being looked at for cleaning up space debris. It seems like such a massive job and probably different ways to go about it, but it always just kind of interests me how we're ever going to take care of that mess. Thank you.
Yeah, that's a very good question. So before getting into that, our biggest lever, as with the trash on Earth, is mitigation. The less we are producing, the fewer pieces we actually have to scoop up. So we have been slacking on that one, so we want to do better. And then several entities are looking into active debris removal. That means going up, having a dedicated mission, trying to grab a piece and bring it down. That's costly, so we cannot do that with most of the pieces, but we're like, okay, even if we can get like 5 or 10 or 15 key pieces that are in danger to be rushing into other things and creating many more pieces, we are making headway. The entity I'm working with that's furthest is kind of Astroscale out of Japan. They had the Alpha D mission. They are now where they had a test object that they released and grabbed and could bring that down. And they're going to have a follow-up mission, but also our own nation, the Space Force and NASA are looking into that. The European ESA is looking into that. The difficulty is, and that was one thing I've been working on figuring out, is that the debris is starting to rotate as soon as it's not actively stabilized, because we have the sun creating a torque on our object, we have the atmosphere, so they start to rotate. So a lot of the technical difficulties is how do you grab something or hold on to something that rotates? How do you get rid of that momentum? Because if you just grab it, then it just spins up the two of you and you have not gained anything. So that's where the research is at the moment, but I think we will see that in the near future.
We're spending a lot of time trying to characterize the environment as well, like especially the smaller scale debris, understanding what's there and how that might impact our assets. It's easier to track the bigger stuff, but some of the little things are a significant risk as well.
I don't think our crowd was this big when you first started, but we're at a solar max, correct? Or something bigger going on in the sun. Can you explain that real quick before we wrap you up?
Absolutely. So the sun has a cycle, and it wakes up and calms down at different times, and we're getting into the solar maximum where it's getting more busy. So we're going to be seeing more coronal mass ejections, more flares, more activity. So it's an incredible opportunity to visualize the corona today during this solar max in this 11-year cycle as we ramp up. And we're in the midst of a heliophysics big year that's a part of as we're doing all of our missions and Parker's closest approach to the sun. The annular eclipse last October and the total eclipse today. So we're really hoping to see some beautiful, beautiful sights, beautiful flares out of the corona as a result of that solar activity.
Another question here in the middle?
In the front.
That is an excellent question. Yeah. No, you're good. Okay, yeah. I need to go look at a map. Honestly, I will get back to you on that one. I'm not sure. I think when I checked the map, it was tracking fairly close to where we were going to be able to visualize the eclipse today, but I don't know, given the conditions that we have, that it's going to be visible. Yeah. Come on.
Thank you for all of that great information. So you were talking about something called solar or space weather. And right now we all know weather here on the ground and on Earth and how it affects us and all the weather prediction that goes on. Right now we're waiting to see the eclipse. So how do you go about predicting weather in space?
You want me to take that? You want to take it?
I can start. Okay. So for us to be able to predict, we have to understand a little bit more about what happens around the corona. So when the sun kind of ejects particles out, they speed up in the corona and then they can come towards the Earth. And so there's different properties that those kind of balls of gas contain. And so we need to figure out how quickly they're coming, what the direction is that they're coming, because sometimes they do come towards Earth, but sometimes they don't. And some of the flares can reach us in a few minutes. Some CMEs take less time than that. So it just kind of depends on a lot of the properties of what that material is and how it gets to us. The NOAA group, they actually already do solar predictions. So you can see some information that they offer, because people go look at that too for even folks that are traveling like on larger flights, because if you're even like going closer to the poles, then you may have like a higher dose of radiation. And so that's something that you can track through NOAA's website. And you can also check about kind of their different energetic particles and how much is happening. I know earlier Carolyn was talking about kind of surface charging, and so we have different things like that that NOAA helps us with.
That's exactly why we have our fleet of spacecraft. That's why we're observing every day to understand what's going on. And we don't know why solar wind speeds up. We don't know why the corona gets hotter. And we are trying to figure that out. There are mysteries about our own star that we still have to solve. And all of that plays into how that energy flows from the sun into our Earth system and drives, energy changes and can impact weather, space weather that flows down through the Earth. And it's an incredible situation as we especially look at sending humans back beyond, going back to the moon and beyond, and how they'll be impacted by the weather in space, and if they need to shield themselves if there's a particular event going on with the sun, or if they are in a place where the sun has had an impact on the atmosphere or magnetosphere of the planetary surface. And I'm going to look and make sure we're
I've got one future scientist question, and then we need to wrap it up because we're a little over on time. Go ahead.
So I was wondering, I've heard during solar eclipses the wind just kind of stops. Is there a reason for that?
Okay. So.
Okay, yeah, go ahead.
Go ahead.
Go for it.
So the solar eclipse, the visible light from the sun is the big thing that's impacted. The energy is going to keep flowing out from the sun. The way that we can look at and visualize some of those solar wind is changing. We shouldn't see solar winds stopping. We shouldn't see that energy flow stopping, but the way that we can visualize the context of visible light and the corona are going to change. And so today, I'm really curious to see what we're going to see if we have any activities. We've had a lot of flares going on and a lot of CMEs going on lately, so this is an excellent opportunity for us this afternoon to take some data and use those sounding rockets and the observations to understand more. It's a great question.
Well, let's give it up for our scientists. This is just the beginning of a very exciting day. We're going to let them head back. I'm meteorologist Angela Buckman, by the way, from local channel 13 here in Indianapolis. I'm going to help facilitate panels coming in and out. I'm going to give you a couple of minutes to stretch your legs, but don't go anywhere. Panel 2 will start in just a couple of minutes. Okay, are we ready for panel 2? We are so excited that you are here today. My name is Angela Buckman. I'm a meteorologist here in Indianapolis at WTHR Channel 13. Oh, thank you. And I'm just here to facilitate, but if you were here for the first panel, and even if you weren't, what I got from it is we get to all be scientists today. So we are excited that you are here. Panel 2 is called Eyes on the Skies and Beyond. It's an infrared eye on planets in Earth's solar system with the James Webb Telescope. Our experts are next.
Good morning, everyone. We're so excited to be here. I am Peg Luce. I'm the Deputy Director of the Heliophysics Division at NASA headquarters. And I have a wonderful panel here who are going to talk to you about how we study stars. We're all here today because of our own personal star, the sun. And the moon is going to give us a rare opportunity to look at it in a way that we usually don't see. But we at NASA and at Purdue use observations, instrumentation to study the stars, and we're going to talk about how we do that. James Webb Space Telescope is certainly something you've probably heard about, but may not know much about. You're going to hear all about it, and many people haven't heard what heliophysics is, so you're going to hear about that too. So first, I'd like our panel to introduce themselves, starting with Jane Rigby.
Hey there, how y'all doing? Good? Awesome. Y'all, I am so excited to be here. My name is Dr. Jane Rigby, and I am the Senior Project Scientist for the Webb Telescope. I work at NASA Goddard, and I am just so excited to be in the path of totality with y'all.
Good morning, everyone. Whoa, good morning, everyone. I'm Dan. Oh, they're adjusting the volume because I can't. Okay, I'm Dan Milisavljevic. There's a filter on me. I'm Dan Milisavljevic. I'm an associate professor of physics and astronomy at Purdue University. We have some Purdue fans in the audience here today. Yeah? So I've been fortunate to lead one of the programs using the James Webb Space Telescope, and I'll be describing some of that today.
Good morning. I'm Asal Nasseri. I'm a program executive in the Heliophysics Division of NASA's Science Mission Directorate, and I'm happy to be here with all of you for my first total solar eclipse.
Really? It's your first? Oh my God! I am really excited that I get to be with you for your first eclipse. How many other people is it their first total solar eclipse?
Wow.
Mine too.
It is super, it is, you're in for such a treat. Oh my God, it's so amazing. I've only seen one and I really want to see another one.
So before we get to the solar eclipse, Jane, tell us about James Webb Space Telescope and how it helps us study distant stars.
Awesome. So in a sentence, the Webb telescope is the most powerful telescope that humans have ever built. It is about 100 times more powerful than anything that came before. It is a telescope that is 1 million miles away from the Earth in a quiet, dark part of our solar system. And it hides in its own shadow. It's always in eclipse, protected from the sun. And the Webb telescope is studying planets in our own solar system, planets in other solar systems called exoplanets, stars, galaxies. And Webb has been able to see further than any other telescope to study galaxies. We are finding galaxies as they looked when the universe was only 300 million years old, right? So we're seeing back in time more than 13.5 billion years. So we can geek out about this. It's a really fun.
Thank you, Jane. And so Dan, will you tell us why is it important to observe stars across the galaxies?
Right. Well, we have our own sun that's nearby, but it's actually, a star of many different types of stars. And as we ask questions like, is there life out there? Are there planets that have some kind of life? We have to understand the stars that they'll be orbiting around, right? And it just so happens, thankfully for us, our sun is fairly stable, but there are stars that are not so stable. So, for instance, stars that are cooler and smaller than the sun may have planets that are closer nearby, and there may be activity that makes life there not so hospitable. So, by studying stars, not just the sun, but beyond and across our galaxy, it helps us understand what kind of planets may be forming there.
Thank you, Dan. Sal, will you please tell everyone what is heliophysics? What do we study? And does heliophysics use any infrared instruments like the James Webb does?
So heliophysics is the study of the sun and how it behaves, why it behaves the way it does, and how it affects everything in the solar system, especially our Earth and Earth's atmosphere. For our first launch in the heliophysics big year, we sent which is atmospheric wave experiment, to the International Space Station. That it's going to help us study our climate, atmosphere, and the effects of space weather for life for us. It has an infrared, wide field of view infrared images that will look at the atmosphere in colorful bands of light called air glow, where in fact, they are there because of what we call atmospheric gravity waves, where you have buoyancy that will push the air up, but the gravity of the Earth will push it back down, and you get these waves in the atmosphere that will have an effect on radio frequency signals, navigation, and communication.
Thank you, Asal. Jane, what are some new discoveries that Webb has made about planets in our own solar system?
So when we built Webb, we built it to look at very, very faint things, right? Galaxies very, very far away. And one of the challenges was to get it to work on, because it wasn't designed to do that, really bright things nearby that move in our own solar system. And so that's been a priority for some of us that we're really proud that we got it working. It's working spectacularly. So we're able to study planets in our outer solar system, asteroids, comets. And to date, the thing that's really been exciting for me, honestly, there's the DART impact. Y'all remember the DART impact when NASA sent a little spacecraft to go hit an asteroid on purpose? We captured that, so we got to see the impact. So we got to see the debris coming out of that asteroid as our poor little DART, that was its job, right? Collided with the asteroid, right? So that was really proud because our folks had to work really hard. That thing was zooming across the sky and it was really hard to chase. One of the things but the thing that's been most scientifically impactful is that we've been able to look at the chemistry of worlds in the outer solar system, and in particular, to look at the moons Enceladus, which is a moon of Saturn, and to look at Europa, which is a moon of Jupiter, and to get little rainbows to see what's going on. We look at the light coming from those worlds, and we can see the fingerprints of the chemistry of what's going on in those systems. And so we've seen these like plumes of water shooting out of Enceladus. And we've done the same for Europa. It's a way to see what's in the oceans of those planets when normally that ocean is locked away under ice. But there are cracks, water comes up, and then we've been able to capture that. And we've been able to show that there's lots of carbon dioxide, which means there's a carbon-rich chemistry in these worlds that we didn't know about before. That's exciting if you think about a wet, warm, carbon-rich world. That sounds a little like our oceans. That's exciting that maybe that is a place possibly where life could exist in our solar system other than our own planet.
So we are really seeing water on other planets.
Water, yes.
Isn't that amazing?
We are definitely seeing water on worlds in our own solar system, moons of planets in our own solar system. And we're studying other molecules like carbon dioxide, sulfur dioxide, methane. We're seeing we're basically it's like having a chemistry lab, but on other worlds, where we're getting to see what the atmospheres are like, what are those planets really like.
That's amazing. Dan, why has Webb been able to show us unique images that we haven't ever been able to see before?
Well, this goes back to what Jane said originally. Webb is basically the most complex, largest telescope we've ever launched into space. So let's unpack that a little bit more. One is the...
Was that a pun? Let's unpack that a little bit.
Oh, or unfold it. Yeah, okay, I'll work with that. Sure, great. Put that in my back pocket for next time.
Keep going.
So, the large size, 6.5 meter. Compare that, for instance, to the Hubble Space Telescope, 2.4. Now, on Earth, we have larger telescopes that are 10 meters in size, but they're on Earth, and they must look through the atmosphere, and that moving air distorts our ability to study the stars. Webb is above that. Webb is also, as Jane said, very far away, 1 million miles away, where it's very cold. Okay? That helps it to operate in the wavelength it's designed to look best at, which is in the infrared. Okay? Its mirror is also coated in gold, which helps reflect that infrared light. So why infrared light? Well, it just so happens that the further you want to look into the universe, the longer that the photons of light have to travel, and because the universe is actually expanding, the wavelength of light gets stretched longer from what made originally as ultraviolet and optical light into the infrared light that Webb can see. And it just so happens that anything that has a temperature has an associated emission of light that can be in the infrared. The instrument itself can. So that's why it operates so far away with the sun shield to keep it cool. I mean, it's something of an engineering marvel that it operates some instruments at 7 degrees Kelvin. That's not a unit we use often, but basically it's only 7 degrees above the coldest temperature possible in the universe. Wow. That blows my mind, right? So it's these kinds of engineering marvels that allow us to get data unlike any observatory we've had before.
And how does that data challenge our current understanding of stellar life cycles, Dan?
Well, one is some of the data are so surprising, it's taking us a while to digest and really understand where we're going from. I can speak personally from my own research on supernova explosions. And let me give you first a warning. What I'm going to say right now will not happen to us with the sun, okay? It just so happens that stars that are much more massive than the sun, about 10 solar masses, they undergo a tremendous energetic demise, okay? If you took all the light, energy that the sun emits over its entire 10 billion years, I mean, that's a lot. You go outside today, you might get sunburned standing out there for too long, right? Imagine all that energy over 10 billion years combined. Multiply that by 100, and that's how much an exploding star, a supernova, will make in 1 second, right? This is an incredible energy source that drives a lot of the evolution of the universe, and this is what I research. And Webb, because it's sensitive to infrared light, can actually access light from the gas that has not been perturbed by shocks of the supernova and allow us to do a kind of an autopsy of the debris field left behind by an exploded star. We can map out how fast it's moving, what it's composed of, and really give us a treasure map of understanding how that explosion proceeded. And again, it's such an important a part of the universe's evolution because of its energy and what it produces for us. These supernova explosions provide the raw materials for life. So the iron in our blood, the nitrogen in our DNA, the carbon in our apple pies, these are all being manufactured in stars and supernova explosions.
So we're really learning about life on Earth from what we see with Webb as it's looking at those explosions?
Many people are familiar with the expression from Carl Sagan, "We are stars." That is exactly correct. And so by understanding these massive star explosions, we're learning about our origin story here on Earth.
That's amazing. Asel, why is it important to study our sun? And why is it important to use observation data collection to study the sun?
Well, the sun is our star. Yes, it's one of the ordinary stars out there, but it's the one that we can actually get closest to and study, and by it learn more about the other stars. But also, it's the main source of energy for us on Earth. The solar wind also, the radiation, solar wind coming from the sun changes space weather and our atmosphere. It can disrupt satellites, communication, radio signals, and navigation. So we need to observe the effects of the solar wind coming from the sun so that we are ready and we know more about the solar system and how the sun affects everything. It touches everything on the solar system. So by observing it and studying it, we learn more about not only Earth, but the solar system.
Thank you, Asel.
Can I interject a point there?
Yes, please.
Sorry, volume is a real issue for me. But pro tip, I always encourage people to get telescopes to observe at night. But you should also strongly consider getting a solar telescope, so ones that designed to look at the sun. In fact, at the booths, Purdue University and others will have solar telescopes set up for you to look. It is amazing how you can see, activity on the sun. You'll see the sunspots, you'll see solar activity around the edges. That'll be in a dramatic fashion today. But a solar telescope is an amazing thing. It's our star, and it routinely is there, visible.
So, Jane, how can you compare what's happening today with our total solar eclipse with the science that Webb is focusing on when it's looking at stars?
Sure, absolutely. So first can I do a pro tip? You did a pro tip. Can I do one pro tip? I really hope that for folks, especially seeing their first eclipse, just soak it in, take your time. It is a chance to remember that we're all part of the universe, that we're on a planet, we're going around a star, that star is going around a galaxy. We're all made of star stuff, except for the hydrogen, which is Big Bang stuff, but either way, it's pretty cool. And an eclipse is a chance to, we all know that, but we have to go do the laundry, and we're out of toothpaste, and life happens, right? And an eclipse is a chance to be like, oh my gosh, that's right. I'm a little sentient being on a planet going around a star. Wow, that's like something out of a science fiction movie. So I really hope you get that today. Something that is also out of a science fiction movie is that we now know of thousands of planets orbiting other stars. We call those exoplanets. And Webb can study those exoplanets, the small subset of them that go in front of their parent star. We call that a transit or an eclipse. And so when that planet goes in front of that star, it makes the star just a little bit dimmer, and then it gets out of the way and the star gets a little bit brighter again, okay? That tiny little dip, which is a couple parts per million, right? So you go from the sun is, if that star is 1 million bright, it goes down to 999,000, right? 999, right? It's just a tiny bit fainter. We can study that transit, that eclipse of that exoplanet eclipsing its star. And we use that, you end up taking, you take a little rainbow when the planet is in front. You take another rainbow when the planet is not in front of its star. You take the difference. And that difference gives you the light of that star that went through the atmosphere of that planet. So you're getting to see light that went through the atmosphere of another planet, and you can measure carbon dioxide. You can measure methane. We've done sulfur dioxide. We've done quartz rain, so sand raining on some of these planets.
Interesting to hear.
And so what we're able to do with that, we've got a live mic. We're studying what other planets are made of, what their atmospheres are like. Some of these planets, there's nothing like it in our own solar system. And we do that using little tiny eclipses of those stars by those planets.
Thank you. We just have a couple minutes left, and Asal, I was hoping that you could tell people a little bit about the science that we're doing today, that NASA experiments that are taking advantage of this eclipse that we're going to experience.
Yes. So we are taking advantage of the eclipse to study not only the ionosphere, which is the charged particle area around the Earth and part of our upper atmosphere, but also looking at the atmosphere of the sun. Because now the sun is not as bright, we can actually see the atmosphere around it, whereas if you look at it right now, you won't be able to see it. So we are going to use aircraft, balloons, sounding rockets, and radars and handheld radios, amateur radios, to study the sun, the ionosphere during the eclipse. We are going to use NASA's WB-57 research aircraft that they will fly through the path of totality to extend the amount of time they can get measurements for our scientists. We are going to send sounding rockets up before, during, and after the eclipse so that they can study the temperature, density, composition of our atmosphere and ionosphere and the changes during the eclipse. And then we have all these other, as I said, the handheld radios, we have balloons, student projects, public scientists and public science projects that are just going to add huge amounts of data to what will help our scientists later on to study the sun, its atmosphere, and its effect on our ionosphere and our atmosphere.
Thank you, Asal. So we are calling this the heliophysics big year. So welcome to the Helio Big Year. It kicked off in October with the annular eclipse of the sun. We launched the AWE mission right after that Asal was talking about. And it's one of the high points, of course, is today. But it actually goes on, it's a big year, it goes on until Christmas Eve, when our Parker Solar Probe spacecraft is flying as close as it's ever been through the atmosphere of the sun. So when you see the atmosphere today, Parker Solar Probe is going to be actually flying through that atmosphere. So welcome to the Helio Big Year. Thank you so much to our guests. They're amazing, and I wish we could have spent more time with you.
Thank you.
Thank you. Enjoy the eclipse.
Enjoy.
Thank you. Great.
Okay, we're going to give you another 5 minutes or so to stretch your legs, but don't go anywhere. We have Neil Armstrong's sons on the panel next. So don't lose your feet. You've got a good one. Okay. It's time to find your seats if you'd like. If you still need to stretch your legs, we understand that as well. But our next session is getting underway. This one is Beyond Apollo, Neil Armstrong's Legacy and Artemis Ascent.
Well, good morning. We got March Madness and Eclipse Madness going on here in Indiana today, so we'll try and finish this panel before the game starts tonight. Just very quickly, because we haven't got a lot of time, I'd like to introduce the people in the panel. My name is John Norberg. I'm going to serve as the moderator. I retired from Purdue University. I knew Neil Armstrong there as my writing about him and when his visits to campus. I'm a Purdue historian. With us today are Rick and Mark Armstrong, the sons of Neil Armstrong and Sharon Armstrong, Janet Sharon. Also joining us is Dr. Jacob Bleacher from NASA over at the end. Just very quickly, so you know a little bit about them, Rick, sitting next to me here, works as a software developer and a consultant, and is also a musician with 3 solo albums released and is a member of the progressive rock band Edison's Children. Next to him, Mark has worked in software consultant and administrative and executive positions with several companies. Dr. Bleacher is a planetary geologist. He is a science advocate for NASA technology and architecture development to enable human exploration of the moon and Mars. So as Angela said, you know, today we're talking about 2 different moon programs, the Apollo program, Apollo 11, which Neil Armstrong was on, and the Artemis program, which is the next project to go to the moon, and it won't be too long before they do that. So just to start off, Dr. Bleacher, Jake, can you tell us where the name Artemis comes from, what that means?
Yeah, that's a great question. Artemis is the twin sister of Apollo in... Louder? Can you hear me now? All right. Yeah, Artemis is the twin sister of Apollo in Greek mythology. So the siblings together exploring the moon, we have a male and a female presence, again from our Greek mythology. And Artemis, one of our goals with Artemis is to increase the diversity of the people who have explored the moon. And so as we go to the moon and onto Mars, that's where we're heading.
Great, thank you. So, Rick and Mark, let's talk about the Apollo program and Apollo 11. And this is probably a good point to stop and point out that today is Mark's birthday. And I think it's pretty...
Thank you all for coming.
I think it's pretty neat that the moon has decided to have a total eclipse of the sun to honor his birthday, and that he's sharing that with us. So that's pretty cool. And it's not your first eclipse, Rick and Mark, is it?
No, and my birthday was on the first eclipse that I saw. So what are those odds?
There are no coincidences. It's all planned. So Rick and Mark, what do you want us to know about your dad, Neil? What is the public getting right and wrong about what kind of person Neil was?
Well, I don't know exactly how to answer what is right, because I'm not sure what that is, but it's a common misperception that he was a recluse. He was definitely not a recluse. He went all kinds of places, all kinds of people. He just didn't maybe notify the media what he was doing, so I think they may have called him a recluse, but other than that, no, he was nothing but that. Or nothing like that.
Just to elaborate a little bit, for example, he and my mother played in a Friday night mixed scramble golf outing every week with, 30 other people from the local town. And after they'd play 9 holes of golf, they would go and to someone's house and they have a potluck dinner, they had a ball. They would laugh and tell stories. This is not the behavior of a recluse, I'm sorry to say. But the truth is that no one that actually knew him would call him such a word. He was, we're very lucky. He was a wonderful person. And as my Aunt June, his sister, often would say, he was the man you saw. So if you saw him and you interacted with him, then you knew him. And unfortunately, the press didn't always get that opportunity, and so they were bitter about it. And I think that's the truth of it. And it's a shame that they put that kind of thing out there, and it just wasn't true.
I agree with that. I know Neil, and every reporter in the country wanted to interview Neil, and there wasn't time to do an interview with everyone in the country, but he talked about every minute of that Apollo 11 flight online. Rick and Mark, most people think it's an incredible experience to meet just one astronaut, but you grew up with astronauts all around you, including the dinner table. What was that like?
We didn't really think of them as astronauts. They were just the neighbors, right? They were just dads going to work. They didn't really see it the same way that everybody else would. So it's a different perspective that's a little hard to explain.
John, we grew up in a neighborhood that was newly developed, and it was created at the time when NASA was bringing in astronauts and scientists and mission control specialists and engineers, because in the early 60s, they knew that they had to make this mandate that was presented by President Kennedy. So our whole neighborhood was full of people that worked at NASA.
And I'm Professor Allie Bramson, and I'm a professor at the Department of Earth.
And okay, so
and I work
everyone
to
was
learn about
in
the planets in our solar
everyone was in it together, I guess is what I wanted to say. And so it didn't feel like a community of that was extraordinary. It just felt like normal life, and that's how we saw it.
How old were you during Gemini 8 and Apollo 11? What do you remember about them? Did you understand the dangers? Was it frightening, exciting?
I was 3, so I'm going to punt to my brother.
Yeah, for Gemini 8, I think it was almost 9, maybe 8, 9, something like that. No, did not really understand how much trouble they were in until really years later, I think. My mom knew, but she kind of kept us from worrying about it. So didn't really think. I never thought they'd get in any trouble that they couldn't get out of. So that was maybe a little naive, but it worked for me. Apollo 11 was 12 for that. So yeah, I remember that pretty well.
Anything stand out in your memory about it?
The launch, of course, I think was pretty amazing, and yeah, I mean we watched the moon landing and the moonwalk, in our living room. I think just like everybody else did, and I think I just expected it to happen. I wasn't surprised when it was successful. I just figured that was how it was going to work out.
The entire week of the mission, our house was full of people. It was customary for astronaut families to host an open house throughout the entire flight. So the door was open, and neighbors and friends and relatives and NASA officials and other astronauts were constantly coming over, bringing over food, and just talking about the mission. And at our house, we had something called a squawk box, which was a way for us to listen to the air-to-ground transmissions, and which were full of jargon, but there was always a knowledgeable NASA person there that could say, oh, well, this is what's happening now, and this is what that means. So it was just really a big open house the entire time, and I think that really helped. It was kind of a community feel, and we were all in it together.
Jake, did the Apollo 11 mission and the other Apollo missions and Neil Armstrong inspire you to go into a career with NASA?
closer to my mouth. Does that work? All right. There we go. We'll figure it out. Yeah, you know, I think it's almost impossible to talk about where we are with NASA now without talking about the Apollo legacy. For me, I wasn't born during Apollo, so we're now in a generation in NASA where many of us who are leading the way weren't around to experience Apollo. But I can tell you for a fact, I work with Artemis, and my favorite thing about Artemis is coming out to panels and talks like this with the public, because every single time I talk about Artemis and what we're doing, I learn about Apollo. Folks come up to me and they say, hey, my parent or grandparent worked for this company that made this bolt that held these two panels together, and they know it. They know it. And to me, that means the Apollo program is alive and an active part of the Artemis effort. And so it's almost impossible to describe the impact that Apollo had on generating this generation of scientists, engineers, artists, you know, everybody that's involved in this effort.
Well, I think we can see that it's easier to fly to the moon and back than it is to get microphones to work here this morning. Rick and Mark, your father once told me that when he said that's one giant leap for mankind, that wasn't the most important thing he said on the moon that day. He said the most important thing he said on the moon was, the Eagle has landed, which was very hard. Walking to the moon was for show. What did they ever tell you about being on the moon and walking on the moon, what the experience was like?
I didn't really tend to ask him too much about it because I knew how much he got asked by others and didn't want to contribute to the noise. I do remember asking him about the low fuel situation in the landing and how close was it, and his answer was, if people don't know, yeah, they were very low on fuel, and his answer was, well, the gauge wasn't really that accurate. and the reason was it's because of the sloshing of the fuel in the tank made that gauge or whatever it was only accurate at a particular moment in time. But you know, he got it down. So I think that was going to happen regardless. At that point, he was going to make it down.
Mark, anything to add?
Well, they spent about 2.5 hours on the lunar surface, and they had a lot to do. Buzz and Dad were setting up experiments. They had to do an external visual inspection of the LEM to make sure that everything looked good there. They had to plant the flag, which wasn't as easy as you might think. It's not a damp soil up there. And of course they had a lot of pictures to take. They had a lot of geological samples to collect, and so they were quite busy during that short visit. But they didn't see much risk in any of that. It was getting it down, getting the LEM down on a stable surface. And not only allowed them to walk on the moon, but gave them a platform to then launch back into orbit after their EVA. So that was definitely the most risky and I think for Dad the most stressful portion of the mission.
Jake, landing astronauts on the lunar South Pole is a crucial objective of NASA's Artemis campaign. Please explain why this region is specifically targeted for human exploration, and does this environment pose any issues or challenges that we didn't encounter with Apollo?
Yeah, that's a really important point to elaborate upon. I will show a quick video here. During Apollo, we understood the lighting at the moon, and we took full advantage of that. If you look at the moon just from your backyard, you can actually see what we would refer to as a lunar day. It's actually about the same length of time as an Earth month. And so in the equatorial regions, they experience 14 Earth days of light followed by 14 Earth days of darkness. And each Apollo mission landed in what we would call the lunar morning. And we knew that they would experience 8, 9, 10 days of continuous sunlight for their activities that they were conducting. But we're going to the South Pole with Artemis. So this is a very different region. We are absolutely standing on the shoulders of giants with the knowledge that we gained from Apollo and over the many years since then. But the South Pole and the poles in general are a very unique and different terrain. It's different places. It's a more rugged terrain. Impact craters have made these circular depressions that you see here, and there are high mountains that we'll be exploring. The thing that's really interesting, though, is the sunlight, and it's very fitting to talk about this today, as an eclipse is truly a celestial dance between the sun, the earth, and the moon. And actually on the moon we will experience eclipses where the earth blocks out the sunlight. But in the lower right-hand corner you can see the south polar region compared to other more equatorial sites. And so when we talk about daytime at the poles, it's not actually the same way you think about a day from the places that the Apollo astronauts explored. The sun never goes up over your head because the moon doesn't have an axial tilt like the Earth does. It's almost straight up and down. And so the moon is turning and the sun is just, I like to say, dancing right along the horizon. So here's a view that we've rendered that shows what it would be like to look at the Earth from the South Pole. One thing I like to point out is when the Earth comes back above the horizon, notice that it looks like it's upside down. Or you could say that the view is upside down if you're standing at the South Pole. So the sun, as I said, is dancing just along the horizon while the Earth is bobbing up and down. And you can see what the light looks like on the surface. It's not sunlight everywhere around you. It's shadows that are sweeping across the area. And so there's a lot to take into account. Now, what's nice about this is that the high topography ends up being places that are in sunlight, and in sunlight more than average. It's one of the reasons we want to go there. We can find places that are in sunlight almost 80 to 90% of the year. So that's very different than the equatorial regions. The other part that's interesting is there are places in permanent shadow. Off to the right of this image is the Shackleton crater. The South Pole is along that crescent of light you can see there. Inside that crater, the floor of the crater never sees sunlight. And so we believe that any water that's been placed on the South Polar region that goes into these craters is trapped. That water is basically a record book of the early evolution of the solar system. So from a science perspective, it's extremely valuable. It could also be a resource. It's one of the most heavy things that we carry when we fly into space is the water. And so carrying enough water to support a mission really increases the thrust that you need to be able to get it off the surface of the Earth. So we really are going to a new place, learning how to explore. We like to say that we're building the blueprint for space exploration. We're building a blueprint for how to leave the Earth. And those first footsteps that we placed on the moon were the first footsteps along that path of building that blueprint.
Great, Jake, we're running out of time, but can you tell us how living and working on the moon is preparing NASA for human missions to Mars?
Absolutely. I mentioned this already. We like to speak about the blueprint. We're building a blueprint for learning how to live away from the Earth. In the time between the Apollo missions and now, we've learned how to live off of the Earth. So at the International Space Station in low Earth orbit, we've now occupied that space station for over 22 years. One thing we like to say is someone who's younger than 23 years old, I bet there's a few of you in the crowd here, don't actually know what it's like to live on an Earth that hasn't had someone living in space. Think about that. It was very, I'm sure, exciting to have someone be off the Earth for a short period of time. Now, children born today don't know what it's like to not have people there. And I like to think about the fact that sometime in the near future, we may be in a situation where young people don't know what it's like that people don't live on the moon, or maybe even Mars. All these lessons about living, landing, operating, they're all part of that pathway that puts a destination like Mars on the radar for us. So learning how to live at the moon, learning how to live in low Earth orbit is all a piece of the story that helps us learn how to go to a place like Mars.
Rick and Mark, last question. How do you feel about the United States returning a human presence to the moon?
You want to start? I think it's super important, both for the the exploration value that Jake was talking about, but also for the inspiration that it provides to people all over the world, just like the Apollo program did. The ROI on the money spent to go to the moon is, you can't even calculate how great that return is. And so, yeah, super important.
There's something called the overview effect that has been expressed by astronauts that have been in space. And they look back at the Earth and they see it as a fragile, beautiful thing that needs to be cared for. And I think that that this is something that is really important for our planet. We need more people to go to space and to talk about it and to write about it and to sing about it and to paint about it, so that more people understand just how special this planet is. When you're out there and everything around you is gray and black, and you look back at this planet and you realize that we have this wonderful atmosphere around us that protects us from galactic radiation, and we have our own renewable food and water sources and water filtration and energy sources that are renewable. This is a special place we live in. And I think that the more people that go to space and live in space and experience that will look back on this planet and realize just how special it is, and that we have to be better stewards of our home.
Great. Well, thank you, Rick and Mark and Jake, for being with us today, and thanks to the audience for joining us. We could talk for hours with this panel, but there's a group of Purdue astronauts waiting in the wings, and you can't hold Purdue astronauts back. So thank you very much, and we'll move on to the next session.
Okay, we're going to give you another couple-minute break, but just a couple minutes because we're going to try to stay on track because we have an eclipse to view here in a few hours, right? And then hopefully a Purdue win later this evening. Up next are some astronauts, and I'll be back in just a couple of minutes to get them on the stage. They don't need any introduction, so I will not introduce them. We'll get right to it. This, by the way, presented by Purdue University today.
Hello, everyone. Thank you for coming. My name is Kate Young. I'm a proud Boilermaker alumna and the host of the This is Purdue podcast. And as everyone knows, it's a super exciting day because of these 5 astronauts next to me, but there's also a certain big game tonight. Yeah. All right. Okay, so I'm going to get started with the intros, and then we'll launch into our first question. Okay, first up, we have Sirisha Bandla. Sirisha is the Vice President of Government Affairs and Research Operations at Virgin Galactic. Next up is Drew Feustel. Drew is a former NASA astronaut, and he's also a Purdue Presidential Ambassador. Next up is Mark Polanski. He is, well, we'll go to Beth Moses next. So she's the Chief Astronaut Instructor at Virgin Galactic. In 2019, she became the world's first female commercial astronaut, as well as Purdue's first commercial astronaut. And we have Mark Polanski. He is the Vice President for Barrios Technology in Houston and a former NASA astronaut. And finally, down there, we have Audrey Powers. She is the Vice President of Mission and Flight Operation at Blue Origin. Audrey is also an attorney, and before working for Blue Origin, she worked as a NASA flight controller. Okay, so we're all about to experience something really big in just about 2 hours. I think the question on my mind, most people's minds out there, what is it like when you finally had your moment to go up in space? And what might surprise people out here, you know, when you were up in space? Is there anything that surprised you all, and could you share that with us?
Yeah, of course. Hi, everyone. So great to be here. So for me, I've wanted to be an astronaut since I was young. So I grew up looking at pictures of Earth from space. So when I finally got to go up and look down at the planet, I mean, from the picture, I saw the planet. It was brilliant, no borders. You see the thin blue line of the atmosphere. You see the matte black of space. But what the picture doesn't capture is the significance, the gravity of it all. No pun intended. That was hilarious. No pun intended. Yeah, but really, that is what it doesn't capture in a picture. And what was surprising to me looking down on the planet and just looking down at everything that I've ever known, every experience, every person, it made me feel extremely small, but it did not make me feel insignificant. And I came back to Earth feeling very empowered, reminding myself that what we do in space really starts with what we're doing here on Earth.
Check, check. We're going to keep going down the line. So my answer about what surprised me most about space was how quickly the human body adapts to living and working in microgravity environment. When we go to space, we just sort of float. Everything floats around us, and it was surprising to me how quickly that could be normalized, and working and living in space was just like being here on Earth and doing the things that we do every day. So that was pretty impressive. Humans have the great ability to adapt to their surroundings.
Check, check. My first flight, what was it like to have that big day, sort of like today's big day? Actually, for me, everyone asks, were you afraid? Especially because our system was new and in test flight and, you know, privately funded and didn't have all the gravitas of NASA. For me, the biggest anxiety was not getting all the data. I flew as an engineer and somehow letting down my team. So fortunately, flight went well and I got all the data. And then to Sirisha's point, I was amazed and had not really anticipated that for our vehicle, Virgin Galactic, we're suborbital. So we just head up and come straight back down. And for me, the time dilation at apogee was pure magic. I didn't expect to sort of feel as if time had stopped. But because we sort of slow down to a stop and then pick it back up and come back down through the atmosphere, the feeling of being unstrapped, completely weightless, not touching anything, in the middle of the ship, looking out all the windows, and coming to a stop and then seeing the majesty that Sirisha spoke about was unlike anything I had ever anticipated, and we are all so infinitesimally small, but so unbelievably important to this planet, which needs us all, especially Purdue engineering, that it was an amazing day.
So for me, the thing that I first felt when I got up there and I got to go ahead and see the Earth from orbit for the very first time, you go ahead and first reflect on the people that are most significant to you in your lives. And so for me at the time, it was my fiance, now my wife, and my family, who had waited all this time to see me, and it was such an emotional experience to go ahead and see that and to know that they were all there supporting me for all of these years. It really meant a lot. The other part, of course, is at this time, there were 8 of us on orbit, so the entire human population, except for 8 people, are on the planet, and that was a pretty astounding thing to go ahead and comprehend. And to answer the question, what was the thing that kind of surprised me the most? That I got there. Which, you know, I'd waited a long time to do that, and as I said, and I don't know about anybody else, it's like, okay, I got this, you can't take it away from me no matter what happens after this. So it was a really pretty cool thing.
The thing that was most surprising to me was the overwhelming sensory experience that it was, and from even the moment of ingressing the capsule on the launch tower and the ignition of the engine, all of your senses just overwhelmed by, and is almost hard to process, and that goes all the way through zero-G, kind of experiencing this weightlessness for the first time, and then through reentry. I just remember thinking, take this all in. Like, really, you know, try as hard as you can to be present in this moment and take all of this in. So I think to Drew's point too, that was, I wanted to keep that with me. I recognized how unique it was, and that my body was able to adapt to all of these things so quickly.
Amazing. So we have a mix of NASA and commercial astronauts with us today on this panel. Some of you have worked within both industries. What are you most excited about when it comes to these emerging partnerships between NASA and commercial spaceflight?
I think, especially now with commercial where it is and NASA doing those incredible missions, it used to be back in the day commercial versus, it almost seemed like it was commercial versus government, but it's really commercial and government. And the capabilities together allow us to do so much more. So what I'm excited about is seeing that capability in space grow because of the synergy between commercial and government. NASA and other national agencies are doing that audacious work, going out and exploring areas and destinations that don't yet have a business case, and they can rely on commercial for suborbital and LEO and use their resources to get us to that next destination. So it's really cool to see them working lockstep, because it wasn't like that in the past.
It's important to remember, of course, that NASA has never existed without private corporations supporting, right? We've always had contractors doing work for NASA. NASA has just been the one leading the way, in many cases contracting out for companies to build spacecraft that we use directly. The difference now is that we're looking for service providers, so instead of doing all that work, we direct the work and provide those capabilities, and eventually we create an economy that is self-sustaining and not just relying on the government, but relies on those private companies to feed off of each other and create those economies of scale. And that's really what I'm excited about now, that we're finally to the point where the technology is meeting our needs and our expectations and our desires and the things we dream about for space exploration, and we create those opportunities. And remember, the money doesn't go to space, it creates jobs here on Earth, and that's what's really important about it, is that we're creating economies that people can then create opportunities for our planet.
Yeah, I agree with both of those. I work for Virgin Galactic. NASA is one of our customers. They fly research on our ship, which actually Sarisha personally did on a flight with me a few years ago.
And they were our first customer, actually, for research.
NASA was our first customer, and actually on my first flight, NASA was flying along with me, automated, and my job was to not kick NASA. So.
She did not kick NASA's payloads.
Thank you. Actually, what I'm looking forward to, I guess, the most is the success of all these years of private and public working together such that private companies can be a service provider selling flights to NASA, and NASA can land people on the moon again. That's what I'm looking forward to.
So I think you're hearing a common theme here. There have been private companies contributing to spaceflight for decades, since the very beginning. The government doesn't do everything with only government employees. It never has. But what's kind of different as of late is that we are now flying people in space who are not associated with government and government astronauts. So real quick, who likes Star Wars and Star Trek and all those kind of movies? There we go, okay. How many people out there actually want to travel in space if they could at some point in their life, okay? Well, the opportunity is so much closer than you think because of what's going on with these private enterprises. And so what we're doing with Blue Origin, with Virgin Galactic, with others, this is just the precursor to what's going to happen. And so the days where science fiction becomes a little more science fact, and the days where more of you will have opportunities, especially for your kids and your grandkids, that's coming because of what's happening now. So, I mean, I think everybody's really in favor of that because it's good for all of us.
Yeah, for Star Wars and Star Trek, everyone claps for this is just, it's a force multiplier for our industry. Getting all of this amazing knowledge and experience together that NASA brings with some of the ingenuity and creativity that we see in the commercial industry. We also at Blue Origin have flown NASA payloads through our Flight Opportunities program, and now we're working with NASA to build the lunar lander that will go to the moon with the Artemis program. And this is just, it's an absolute force multiplier. You cannot possibly achieve in a silo all of the things that you can achieve when you partner with other like-minded and diverse folks and agencies and companies. So to think that we're in a space where 600-ish people have ever left this planet, and that number is just going to absolutely multiply in a huge way, much more rapidly than we've seen in our lifetime.
Amazing. A lot of people believe the total solar eclipse is best enjoyed with a group. We have a lot of people here today. We're at the iconic Indianapolis Motor Speedway. What does this event mean to you all? You've spent your whole careers, studying space, exploring space. What are you looking forward to experiencing today with all of us out here?
Yeah, I mean, it's an incredible, events bring people together, and it's really cool to be here for a celestial event, because we're all space nerds, to bring a very diverse group of people together. I mean, we've got engineers here, of course, but we've also got politicians and lawyers and artists all here for the common event of seeing the eclipse. So that's really what excites me, is coming together with that base foundation, getting to know everyone that's here and what this event means to them. And we at least have that common thread to kick off relationships, and that common thread today is space, which we're all really excited about. And the one other thing I'll add is it's kind of like the first question. It's about the experience. We can see pictures of the eclipse, we can talk about the eclipse, but until you've seen it, you've seen a total solar eclipse, it's really hard to describe what that feeling is, and it really puts into perspective what goes on up there, whether it's infrastructure we put up or the physics of everything that's out there in the universe affects our lives. And this is 3 minutes where you'll get that, and you'll see that impact, and you'll feel that impact of space.
Okay, so for me, I'm a huge motorsports fan. Anybody who knows me and has followed me, I'm really into motorsports. So to me, this is like the perfect trifecta. We've got Purdue University, our alma mater, all of us up here. The IMS, which is the icon, of racing, and space, the exposure to the eclipse and seeing what's happening with orbital bodies around us. So to me, this is perfect. As a kid, I either wanted to be an F1 driver or an astronaut. I figured out one of those things, hoping today to figure out the other half. But it's just great to be here and a great place to do it.
It's not too late to be both.
Well, let's see, for me, I think it's somewhat ironic, fate loves irony, that, all 5 of us went to space because mankind figured out how to, engineer something spectacular and control Mother Nature. Well, today I think Mother Nature's in control and we're going to all be humbled.
So if I get philosophical for a second, when I'm thinking about what's going to happen with this eclipse, and I'm looking at, the tens of thousands and more people that are going to be just here, a lot more over throughout the city and throughout the path in this country. I mean, they're going to have millions and millions of people watching. Some of you are watching because you're into astronomy, you're into science, you like that stuff. But a whole lot of people are going to be doing it because it's this seminal event that doesn't happen that often. And you're going to go ahead and you're going to look at the sky and just think about science in a way that maybe you don't kind of think about it. And so what I'm really hoping happens is that we're going to go ahead and have a lot of people, especially a lot of kids out there, who are going to see this, and it's going to motivate them to realize that there are things that happen off of this planet, and there's opportunities off of this planet, and that they can go ahead and be a big part of this, which is going to go ahead and make our country and our world a better place.
We've all had the opportunity this morning to meet an amazing number of people from here in Indiana and at Purdue, but people from other countries, folks who have come from far and wide to experience this event. And I think the feeling of unification and the fact that through no fault of our own, this perfection of the universe is going to be on display today. And that we're all just here able to witness it together. There's this wonderful feeling of unity that I think we've all experienced with the folks that we've met this morning, and just a really wonderful a wonderful event to be able to observe and honor and enjoy and learn about this perfection of the universe.
I mentioned earlier it's a very special day for Purdue University. Gene Cernan, Purdue alum and the most recent astronaut to walk on the moon, said, "Why are there so many astronauts from Purdue? What are they doing over there in West Lafayette?" So we're going to talk about that. What would you say, how would you say Purdue, prepared you for your successful careers? Any favorite highlights or memories from your time at Purdue?
So I literally went to Purdue because they had the most astronauts, and Neil Armstrong went there. I didn't even apply to a backup school, which was kind of dumb now that I think about it, but everything worked out well for me. But it was inspiring to me. I mean, not to embarrass, but at the Armstrong Hall, there's a wall of astronauts, and I would go by Drew and Mark's face while I was studying there every day. I didn't touch them or anything, it was weird. But I did look at you guys. I'm like, one day. So really, I mean, that kind of inspiration to, follow in the footsteps of just really incredible alumni, was something that kept me going, because engineering was hard. I found out really quickly that I didn't even know how to study when I first joined freshman engineering. So just looking at some of the achievements really helped keep me going, and seeing what is after graduation and how this education I'm going to get at Purdue is really going to, align me for success. And I mean, how awesome that we have such incredible graduates that are literally teaching people that the sky is not the limit. It's just the inspiration we all need.
I also have to note, Sarisha's face is now up on campus. She humbly left that out.
And your face will inspire others to do the same thing, and that's the beauty of it. I, too, went to Purdue because I believed in its ability to create astronauts and create opportunities. And Purdue has so many graduates around the world, not only in our country, but around the world, that are in aerospace and exploration, that I think it just supports the development of people that then want to get into actual human spaceflight. You had the panel just now with the Armstrong kids. Neil Armstrong and Buzz Aldrin, led the way to the surface of the moon with Mike Collins. But knowing that Neil was there and knowing that Gene was the most recent person on the moon, I think that inspired all of us. So just like you were inspired, I was inspired by thinking about them, and led me to Purdue and thought about the opportunities that it created. And I think that does the same for people wanting to get into industry and do other things. It may not just be exploration, but Purdue is such a great school, such a great institution for this state and the country that it just breeds excellence, and it shows.
Yeah, absolutely. Likewise, I knew of Purdue's legacy, both its relation to NASA and its relation to space explorers, and was drawn to it, and it was my first choice school as well. You asked, or maybe Gene Cernan asked, what's happening out there in West Lafayette? Honestly, it really is, and thank you to the current and former presidents of Purdue, a magic place. I had no idea until I was there. We all worked like dogs, slaved at our homework overnight, many, many all-nighters. But it's an environment where you learn humility, teamwork, and support, as well as the craft that you're there to learn. And I came out of there a much more well-rounded individual than the idiot kid who started there. And so I think there is magic in West Lafayette. Thank you to Purdue.
Okay, so 3 really eloquent responses. So, true confessions. I had no clue that Purdue was a place that astronauts went to. Okay? I didn't know anything about Purdue. I kind of came to Purdue by accident. I grew up in New Jersey, and I found Purdue through a friend, and I applied, and I'll make the story short, but I came to Purdue. I started out as a physics major. And after a year, I found that I liked physics, but physics did not like me. So then, when I was finishing my freshman year, and if anybody's here from Purdue, you might have heard of a place called Cary Quad. And that's where I lived as a freshman and a sophomore. This astronaut came to give a talk at one of the common areas, and the guy's name was, just as Kate said, Gene Cernan. And so I got to meet a guy who had walked on the moon. And wow, did that go ahead and set me for a loop, like, I want to be like that guy. And so that started me on a path. And every time that I would have a reunion, I would remind Gene in a form like this how I met him when I was a freshman, and he inspired me, as some older guy. So Shirisha, thanks so much for doing that to me in return. Okay, but it's funny, and like Drew said, it's gonna pass on, right? Because somebody's gonna see one of you folks and be inspired by that. But like Beth said, I started out like I didn't know anything about this university. Well, I learned a heck of a lot in a very short period of time. And there's a big difference between what you start out as a freshman and what you wind up as a senior. You grow so much. And yes, Beth, this university gave me everything that I needed to become successful and get out there and set the foundation which allowed me to go ahead and get there. And so I have undying gratitude to Purdue. And let's go kick some butt tonight, too, okay?
Well, Purdue gave me a career in human spaceflight. I mean, it is that simple. It's what I wanted from a very young age. And I knew a lot of astronauts went to Purdue, and I said, even if I don't get to fly in space one day myself, I want to enable human exploration of space, and this is the school that I need to go to be able to do that. And Purdue taught me, to Sarisha's point, it was real hard to get through Purdue engineering. And you get to graduation and you think, man, I survived that, I got through it, I did it. That is how hard some of this stuff is that we are doing. So those challenges and all of that, really hard work, that has followed me my entire career, and that is what it takes to expand these barriers that we're all talking about and to explore space in this way. So it taught me determination, it taught me stick-to-itiveness, it taught me that there is absolutely no way I can do this on my own, I am still close friends with the people that I went through Purdue engineering with. I relied on them and they relied on me to succeed when we were engineering students, and they are still my colleagues and my mentors and my commiserators now that we're all out in the industry, and we continue to succeed together even though we're all at different companies and sometimes we're at the same company. So all of those things that I learned at Purdue as far as how to survive and succeed, I have absolutely relied on it my entire career.
Boiler up. Okay, this is going to be our last question. I want to know what's in the future for you all. What's your next giant leap?
I just love where I am right now because I worked my entire life to get to space, especially I think at the time was non-traditional. I think it's now becoming, I think that notion is going away, but I'm now in a position to help enable more and more people to go to space, especially scientists and researchers. So I'm really excited about that. What my next giant leap is, I'll be totally honest, I don't know. I've been working to go to space my entire life, and then I did it, and I was like, okay, what's next? And I did the same thing. So it's actually kind of liberating to have a blank piece of paper to kind of determine what I want to do, what I want that next giant leap to be. But I'm not rushing to it. Thanks, Drew. My biggest supporter.
I'm like you, I don't know what's next. After a 23-year career with NASA, I'm now working in the private sector and supporting Purdue University as well as a presidential ambassador, along with my wife, Indy, who's also a Purdue grad. And so our next giant leap is just to continue to share this story, give back to not only the university, but also continue work in human spaceflight and try and help to enable and take advantage of that low Earth orbit economy and that lunar economy that we're all working towards now and have been for the last 5 to 10 years. So see what happens.
Well, I've kind of got two short answers. So I've flown 6 times. 4 of those times were within 5 months last year, and once was on 2 hours' notice. So the next thing I'm going to do is take a vacation. And then after that, I think, like everyone here, I want to continue to contribute and spend the rest of my life helping human spaceflight, as hard as I can, and so I'll continue doing that.
So for me, I've had the longest time since my last space flight from everybody up here. So it's been almost 15 years since my last space flight. And so I've already made that transition from flying in space to knowing that I'm going to go ahead and have a career where I'm more, feet on the ground. And so for me, I'm going to continue doing what I have been doing, which is to go ahead and support industries to be successful so that we can continue exploration of space. I support NASA's goals to go ahead and have public and private enterprises for exploration on the moon, to get onto Mars with a human being, and to go ahead and continue and do that. And then on a personal level, I think for my wife and I, our big adventure is figuring out whether our son's going to go to Purdue or Texas A&M, right? So we're working on that.
Purdue.
Well, I'm still working on the New Shepard program at Blue Origin, and we really want to make this routine. So figuring out how to reuse every single piece of our booster and our spacecraft and fly it routinely, like every week. That's what we're trying to do, and we're using the technology. Something that really excites me about continuing to support this program is we are using technologies on New Shepard to inform the future programs. So our lunar program that will help NASA land people on the Mars, people in cargo on the on the moon. We are using those technologies on New Shepard during our flights to test them and to vet them before they fly on other missions. So I like that kind of feedback loop that we're able to enable on my New Shepard program. So that's what I'm most excited about.
Thank you all for sharing. How cool was this? We got to spend some time with 5 astronauts. Can you give them a round of applause, please? Thank you so much. A quick reminder, This is Purdue is available on Apple Podcasts, Spotify, YouTube, wherever you get your podcasts. This is going to be a podcast episode, so you can listen to it again and again. And quick reminder, too, that they are going to be signing autographs at 3:30 right back in here at Gallagher Pavilion, along with some IndyCar drivers, so don't miss that. And finally, boiler up, and let's cheer for our men's basketball program tonight.
Boiler up.
Thank you all.
Oh, you're sweet. Thank you. Want these? Here? And do you want the clicker then? Yes. Thank you so much. Good.
Yep.
Okay, looks like we lost a few. So those of you in the back, if you want a better seat, come on up. We're not quite done. We've got one more panel left that includes a combination of race car drivers and astronauts. So you're not going to want to miss it. Okay. We have made it to our final panel of the day, and you are in for a real treat. Astronauts and race car drivers here at the Indianapolis Motor Speedway.
All right, well, good afternoon, everyone. While we are getting seated on the stage, first of all, we appreciate all of you being here. My name is Holly Ridings. I'm excited to host the panels, astronauts, race car drivers. I came from Houston, Texas. We're really excited about the weather here for the Eclipse, because if you've looked at the weather, like Texas is really terrible, so we're excited to be here. In Houston, I'm responsible for building a space station around the moon that's part of NASA's Artemis campaign. The name of the space station's Gateway. Before that, I had the opportunity to work in mission control in Houston as the first female chief flight director for many, many years. And so, thank you. And so one of the really exciting things about doing those jobs is you get to meet a lot of really amazing people, talk across industries. And so today we're going to talk some about flying in space and also driving race cars and the similarities and differences, and then some of the innovation that's going on. All right, so I'm going to introduce our panelists. Kind of at the very end down there, we have Megan MacArthur, astronaut. She flew in space STS-125, and so that was the mission, one of the missions to service the Hubble Space Telescope. Pretty awesome. She caught the Hubble with a robotic arm, which is really cool. And then had the opportunity to fly again just recently, going up to the space station on a SpaceX Dragon and living and working on the space station for a long duration mission. So she is our astronaut. Next to her, we have Lizzie. And Lizzie, we're very excited, is on our panel. She was a student at Purdue, so very local, and now works as a systems engineer for the Aero McLaren team, and she'll get to talk to you a little bit about how she got where she is today. All right, then we have Kurt. Oh, go ahead. All right, then we have Kurt Busch, who drove NASCAR for many, many years, just recently retired, although I was listening to him talk, and he doesn't sound like he's very retired. He was talking about going to team meetings and coaching, so had the opportunity to race in all the NASCAR series. Told me he raced once here and actually might have beat one of the other guys on the stage. So as you could tell, the race car drivers had an awesome time, just like we do at NASA, giving each other a really hard time. So Kurt's going to be with us. Then we have Will Power. Go ahead. Will had the distinction of winning here in 2018 at the Indy 500. Currently, obviously, racing, right? The season just started, only 1 points race. Apparently 2 events, but only 1 points race. So you'll get to see a lot of him this year following along in the Indy series. Next up, we have Alex Rossi, who is also currently driving for Aero McLaren. Oh, I see some cheers. You guys probably know this, but he had the distinction also of winning here on the 100th running of this race in 2016 as a rookie, right? And so it's pretty awesome. Then down at the end, we have Lynn St. James, and she is a legend in racing. Oh, go ahead. They know you. They know you. This is awesome. She, of course, was one of, I think, just 9 females to race in Indy, 1992, the second female to do it, Rookie of the Year, and now has a group that's doing women in motorsports and trying to really help improve the diversity and the opportunities for women across all of the motorsports, both working with the teams and then all of the individuals coming through the system. So we're really excited to hear from her. All right, so we've only got 25 minutes. I probably took up 3.5 or 4 of it, and we've got a lot for these to say. So we are going to jump right into questions. I realize that folks are still coming in the back. And so you guys just come on in and sit down. It's not going to bother us at all. I know we were a little behind turning the room over. So you guys come on up to the front. We're happy to just keep talking while you walk on in. So with that, we're going to start with the first question down at the end to Megan. You know, just if you look at race cars and racing and drivers, and then you also look at spaceships and human spaceflight and astronauts, there's a lot of similarities, a lot of things that jump out at you between the two different groups of people. We were actually talking about some of it backstage. So Megan, maybe for you, what jumps out at you in terms of similarities between our worlds that we have represented up here?
Thanks, Holly, and let me say just hello, and we're really excited to be here. I'm here with my 10-year-old son, and so I asked him this question last night. What does he think that race car drivers and astronauts have in common? And he said, well, you go really fast. You both go really fast. You both need a lot of training, and sometimes you fly. So William told me that's actually usually unintentional when that happens for them. But yeah, so I think there's several things that jump out to me as being probable similarities. And one, of course, is the way we rely on technology. We use cutting-edge technology to do things that humans otherwise aren't suited to do, right? So exploring space, doing research in space. We have huge teams of engineers that work really hard to make our missions possible. And that, I think, is the second thing that really jumps out at me as being a similarity, is that we are just a member of a team as astronauts, and we're maybe the most visible member, similar probably to race car drivers. You're a very visible member of an extensive team, right? That every single person working really hard, working hard to do their job right, to keep us safe, to make us successful. So those are some of the sort of obvious similarities that I see. And then I think we'll also hear, I'm interested to hear, Lizzie, from you. One of the things, when you're living in space, you're in space for 200 days, or the space station, of course, has been in space for over 20 years. When we're building hardware, we have to have hardware that's really durable, that's going to last, that's going to be resilient, and that's going to be resilient to me fixing it. So, because we can't call in the specialist, we have to be able to do a lot of that work ourselves. And so really making sure that your hardware is resilient to the environment that you're expecting it to work in, to make sure that you're successful and safe, is kind of another similarity that I see.
All right, well, thanks, Megan. Let's see. So maybe, Kurt, I'll go to you next. From the driver's side, do you see same things, different things? Like, what is, looking at the space world from your perspective as a driver, what does it look like to you?
It's very similar, and it's such a powerful combination when you have all of the departments and everyone that's working together, and they find that synergy, and you find that zone, so to speak. And a lot of it is done back at the race shop. But the biggest thing for me, like when I hit the racetrack for that first lap every weekend, and I'm driving down into turn 1 at 200 miles an hour, that's that trust. That is what you find in the people's effort and the quality that they're building into the race cars. And with the teamwork, it's all the way back to the wind tunnel. You have the engineering staff, you have the pit crew guys. They have to do their job, jumping over the wall and getting the pit stops done in a quick amount of time. There's again, just the safety protocols that we go through. I'm sure it's way more stringent as an astronaut, but it's so very similar. You have to be on call, ready to go at any time. You have to adjust to all the changing circumstances. I loved weather as a kid. I loved meteorology, and when I got into racing, you learn so much more about the different elements that come into play for finding speed out on the racetrack. And then when I would jump to IndyCar or to drag racing, you find even more things that continue to teach you how to be better in all areas. And so, like anything else in life, once you stop learning, you're stagnant, and you always have to find ways to continue to learn, continue to adapt, to evolve. And as a kid watching the NASA program back in the 80s, that's why I'm a big fan, and that's why I'm here today. And also at the times that I've spent in Daytona around our races, there was launches down at Cape Canaveral, and so we'd always go down there to try to check out a launch. And most of the time it was a big party, but we had a lot of fun trying to learn more about space, and it gives you more motivation to go to the different places to absorb NASA and the Smithsonian's, of course, that are in Washington, D.C. So I'm a fan today, but it's really neat that Indianapolis Motor Speedway put this on.
Well, let's see, Lizzie, since you're sitting in the middle, I'm actually going to go to you next. Because, Megan talked about the teamwork and, so did Kurt. And then actually weather, we could spend probably 3 hours just talking about weather between spaceflight and racing. But what does it look like from your side? Because the team, like what's the preparation? When does it start? We just see the race at the end where you go around the track a bunch. Like explain that to us.
Yeah, so most of the time you guys on the track see the car in its final product. But the months and months that go into prepping not only our Indy 500 cars, but our cars for all of the road course and street course and short oval racing we do. We've been prepping for the Indy 500 for months now, and we're finally getting the cars in the final stages for the test this week. But from my side, from the systems side, I'm really concerned about the electronics, making sure that the car is as healthy and as safe as possible, and making sure all the sensors are reading accurately before we go to the track.
Well, we were talking about the preparation. So I think one race in, 2 events. It's a very long race season. You start months and months before, but then you race almost every week. This is an off week, so you guys got to join us. But like for you as an individual, what is it like trying to get ready for the race season and then stay at kind of that level of performance throughout many, many, many weeks?
Yeah, I mean, I think people don't realize how physical our cars are to drive. We pull a lot of Gs. I think under braking we pull 5 Gs. I know when we had really high downforce at Phoenix, we were pulling 6G in turn 1 there. So you have to train very hard. You have to train a lot. You have to train hard. And literally when the season ends, in September, you're immediately starting your off-season training, getting that base good, doing some long cardio work, start doing weights, put on a bit of weight to build some muscle. I'd say during the season you get car fitness. That's what I call it, car fitness. And I don't think there's any training you can do that helps that. I mean, you've got to be in top shape, but the car fitness is a big deal because you'll be super fit, whether it's swimming, running, rowing, whatever you do. Everyone has a different program, but you have to be top level cardiovascular strength, all that. But when you get in the car for the first test, you go down to Sebring, you test. I mean, your glutes are burning, your heart rate's way up there, your arms are aching on your first run. So that kind of shows it's just the forces, the G forces, those lateral G forces are so hard to train for. And so you get car fitness as the season goes. But you still got to maintain the fitness in the gym. You still got to be in the gym training in between races every week just to maintain that level of cardio strength. But we also have simulator. You have simulator time, which is pretty good. It doesn't simulate G-force, but I mean it's the same weight as the wheel. You're training in the at the circuits that you go to. You do a lot of that in the off season, and you do that before every race. You go to the actual track you're going to race at in the simulator, and I mean it is exactly the same. Like seriously, when you sit in the simulator, you're sitting at Long Beach and you're actually looking at the buildings, and it feels like you're there, and the car feels very, very, very close. So massively important. I mean, if you're not fit, you'll make mistakes. You won't think as well. Your decision making goes down. It matters. It really does. It matters to be fit because you'll simply be slower if you're not.
Yeah, so Kurt, do you guys do the same kind of simulations on the NASCAR side as well?
Yes, absolutely. And like Will says, the track mapping, the bumps in the track, the ambient or the architecture of the buildings and things, it's so realistic. But yeah, we don't quite simulate G-forces. That's the toughest thing to prepare for.
Yeah, so Megan, do we have spaceship fit? This is what I want to know. We have car fit. I've never heard of spaceship fit.
That term for sure. It's very important for us to work out when we're in space because if our bodies aren't loaded when we're in free fall around the planet, our bodies aren't loaded like they are here walking around on the surface of the Earth. And so our muscles will start to atrophy and our bones will start to dissolve. And so if you did nothing and you spend 200 days in space, your bodies are going to be pretty unhappy when you get home. And so we have time on the schedule every day. for working out. But I think we should rename that Spaceship Fit. I think that's a fantastic idea.
We're totally adopting that. All right, let's see. So, Alex, for you, a little bit different question. So, Rookie of the Year 2016, you won here. We talked about that. So that's 8 years in. Curious about, innovation and technology, how things are changing. And then I heard you had a really good podcast that you talked about all kinds of stuff. So, like, what's coming down the pipe? What does the future look like to you?
Well, I think what's very cool for the IndyCar side of things this year is we're introducing hybrid technology. So obviously, we've got two different manufacturers in the championship in Chevrolet and Honda. A lot of where consumer cars are going are towards hybrid and electrification. So there's an importance to our partners to have a product that represents their brand and their trajectory. So hybrid systems are coming into the car at some point in this season, actually, which is going to be exciting for everyone to watch. It'll add a whole new dynamic and element to the racing and the strategy and obviously the performance of the car. IndyCar is also, we're the only race series in the world to be on 100% renewable fuel, which I think is very cool and certainly very innovative in terms of, we have engines that, creates 800 horsepower at their peak, and it's on a fuel that's renewable. So that's awesome. And then also 2 years ago, Firestone actually introduced a tire for our street courses, so the races that we do through city streets. One of the compounds, so we have two compounds, the softer compound, so the higher performance tire is actually, the sidewall is made from a Waiuli plant, which is again a renewable source of rubber, and it's the first tire manufacturer in the world to do something like that. So IndyCar in a lot of ways is looking to the future. It's important for our brands and our partners to definitely have a mindset to be environmentally conscious, and we're doing it in a lot of different ways. So that's cool. Obviously, we're all about going fast and making a lot of noise, and that's something very similar to rockets, I think. But yeah, for those that haven't been to the Speedway before, it's this is our home. This is what we love coming here for any sort of event, and it's certainly amazing to see so many faces here for what is going to be a very special moment in time here in a couple hours.
All right, well, thank you. I appreciate you doing the science part, right? So solar eclipse, renewable energy. It's all about the sun. One of the things we're very focused with spaceships as well is, we like the smoke and fire part. In ours, it's maybe more controlled. In you guys' case, maybe smoke and fire is not super great. For us, we have to do it to get the spaceship off the ground. But certainly lots of different types of fuels on the spaceship as well, right? We've got a lot of commercial partners out with NASA that are experimenting with different ways to do that. Let's see. So we'll switch gears a little bit one more time. So Lynn here, as I said in the intro, one of the pioneers of women in motorsports, had an opportunity to drive the Indy cars. And so for you, maybe just give us a sort of a sketch of, what it looked like when it started, what it looks like now, maybe what you then want it to look like in the future, and what you're working on.
Thank you. I guess I'm old, and so the way it was, but I'm not a historian. I'm not Donald Davison, so I don't really know all the history. But I can say that, I was fortunate to find my passion. And the one thing that I do say is that the car doesn't know the difference. It doesn't really know the gender, the ethnicity, and we're not robots yet. I worry a little bit because I think a lot of the advancement of technology with the autonomous vehicles that are out there, and I know there's some autonomous racing going on with Indy cars, but the human factor is still, with all the technology focused on the vehicles and the dynamics and all of that is fantastic, and I think it truly does create a lot more overlap with the aviation and with aeronautics. But at the same time, I think there's still so much to be learned about the human factor. Not just the physical fitness, but how the minds work and how they fit with the team and the human dynamics of how teams work. I don't know these guys very well, but I can tell you that there are times that I'm sure Alex will be with a team and be able to get the most out of the car and the most out of himself. And those are sometimes very hard to define. I don't know how the technology or engineering can do that. But if you look at each individual driver, and I know even my own career where everything just gels and you really are able to bring the best out of yourself and out of your team. And I still think that human factor, I love technology. I love the fact that the cars are going faster, not all that much faster than we did back in the 90s. But the fact is that it's advancing technology, but I think there's still opportunities for the human factor. And if I were young out there thinking about what I would want to do as a career in my life, I would really want to do not just about health and fitness, but just about how human beings work and how to bring the most out of human beings particularly in a team environment. And when you then also are dealing with technology, which of course is advancing, the blend of advancing technology, of the human dynamics, and then how to bring the most out of human beings. And I still think that's an open door to be able to explore more, and maybe not enough emphasis on that. And I think more women and more people of color, more people from different diverse populations would have opportunities then to, it wouldn't be such maybe an expectation of a cookie cutter of what a scientist should look like, what an engineer should look like, what a race car driver should look like. It would be a much more open field. And I guess that would be my wish for the future, is that it would just be much more wide open for people that have the passion and have the skill and can develop the skill and bring the best out in every human being on Earth.
Absolutely, thank you. So maybe, Lizzie, I'll ask you to follow, right? Because you're kind of at the very beginning of your career. This was like a dream and a goal. I think your degree is motorsports. Like, it's just like, that's a cool degree. Like, I want to go to school for motorsports. And so, like, what does it look like to you, being female, and then also just, people always said to me, well, Holly, what's it like to be the female chief flight director? And I always wanted to say, I just am the chief flight director, right? I worked hard, and we want to get to that point, but at where we are now, we're still talking about it a little bit. So what do you think?
Yeah, it's definitely an interesting question because I don't know what it's like to not be a woman in motorsports, because I always have been. So it's definitely a question I always find very hard to answer. But like Lynn was saying, I didn't come into motorsports to be a female in motorsports. I came into motorsports to be an engineer. And I wasn't hired because I'm a woman. I'm hired because I'm a good engineer. So I think it's important, as I see more females coming into the paddock, which is always extremely exciting for me, that they know that your voice matters and that you belong here and you should be up here. And don't let anyone tell you that you shouldn't be up here, because we're here for you. We've got a great support group, and I hope that I see you guys up here in the future.
All right, we have like just a minute or two left, so we're going to do lightning round, which means you start at the end and everybody goes down, and then you get to say like, a couple of sentences, something you want to leave the audience with. So Lynn will end with you. So you got time to think. So, all right, Megan, ready, go.
Sure. I just want to echo what both Lizzie and Lynn said, that the more people we have thinking about solving these difficult problems, the more people we have working together, bringing their innovative ideas and their unique backgrounds, the better solutions we're going to get. So I'm looking forward to seeing what the future brings for both industries.
All right, Lizzie, go.
Be curious, ask questions, figure out how the world works.
Excellent. Kurt, go.
It's about work ethic, commitment, and being in that top 1% and pushing yourself to become better and better.
This is getting harder.
I would say find your passion and work hard, follow it. Anything can happen. Anything, believe in it, and it will come true, I promise you.
Honestly, I'm just pumped to watch the moon go in front of the sun for the first time since 1869 in Indiana. So, let's go.
I thought it was easy. It's getting harder now, but really believe in yourself. Find a way to believe in yourself, and then find other people. But find your passion, and then just believe in yourself. Don't let anybody stop you.
All right. Thank you. All right, my 2 sentences to leave you with is just great people, right? I just met some of these people. We all met each other like an hour ago. They are amazing, and you can form a team from anywhere if you all are just excited about what you're doing. So thank you guys for being a wonderful panel, for taking your time, and we appreciate you guys listening. Thank you very much.
All right, that concludes the fun of the morning. Things are just getting started. Be sure to come back here after the eclipse. We will have race car drivers and astronauts signing autographs. That will happen at 3:30 in this building. So come back after the eclipse. Thank you to our moderators, our panelists. I don't know about you, but I was here the whole time and I learned a lot. So we were obviously very grateful for their time. And thank you for being such a great audience. Opening ceremonies, by the way, get underway at 1 o'clock. Enjoy your day.